In this video, we'll discuss how to reduce noise in a dataset. As mentioned before, noise can obscure the overall trends in the data or introduce bias, leading to a biased model. Therefore, when working with a new dataset, it's always a good idea to analyze its noise levels and try to minimize noise as much as possible. For noise reduction, this lesson focuses on smoothing data point distributions and detecting and removing outliers. However, this doesn't cover all aspects of noise, such as repetitive or redundant data. Those issues are more straightforward, like checking for duplicate data points by iterating through the dataset. Although we won't specifically highlight these steps again, they remain a critical part of data preprocessing. Make sure to keep them in mind when working with your datasets. Let's start by looking at data binning. Data binning divides continuous data into a series of discrete bins or intervals. Simply put, we group nearby data points together and use certain characteristics, like the average, to represent the entire interval. In doing so, we ignore the details of many individual data points but preserve the overall distribution of the dataset. By using data binning, we can simplify the data, reduce noise, and emphasize the overall trends, making the dataset easier to interpret and analyze. In this example, the blue dashed line represents the line chart plotted using the original data points. As we can see, the blue line has noticeable fluctuations, which makes it harder to analyze the overall trend of the curve. Relative to the dataset's general pattern, these significant fluctuations are considered noise. In many cases, we care more about the direction of the data rather than the extent of the fluctuations. For instance, we may be more interested in knowing whether a person's income is increasing or decreasing, rather than how much it increases or decreases. Of course, for some tasks, the exact value is critical, such as predicting a person's exact income. The orange line in the example is a simplified version of the blue line. We divided the original dataset into 10 intervals and plotted only a few points within each interval instead of every single data point. This produced the orange curve, which has less fluctuation. Clearly, if we only care about the data's general direction, the orange curve can help us find an answer in a shorter amount of time. Similarly, before diving into the details of data binning, let's first look at some general knowledge, like why we use data binning in the first place. Take a moment to think about this question before we go over the answers. This question is actually a free response one, so there isn't a fixed answer. As long as you provide a reasonable response and can analyze your reasoning, that's perfectly fine. The most obvious reason for smoothing is to reduce noise. By applying a smoothing operation, we average out some of the highly fluctuating data points, which helps reduce the overall noise in the dataset to some extent. In this example, we calculate the average of every 4 data points from the figure on the left to produce the dataset shown on the right. As you can see, the right figure removes many of the highly fluctuating data points while still preserving the overall trend of the original dataset. To achieve smoothing, we sample from the continuous data points, which reduces the total number of data points. As a result, this process effectively lowers the dimensionality to some extent. We can use this same example to understand the concept of reducing dimensionality. By reducing the amount of data, we significantly lower the complexity of the learning task. What we really need is the essential information, not the raw data itself. By applying data binning, we can enhance the robustness of the trained model. To illustrate this more clearly, in this example, we've artificially added some very noticeable noise. For comparison, let's assume that the original dataset has no noise or only minimal noise. This contrast allows us to better observe the effect of data binning on handling noisy data and improving the model's performance. When training with this noisier dataset, we're likely to end up with the green line as the trained model. As you can see, this model is influenced by the noise, so the green curve fails to capture the overall trend of the dataset accurately. As a result, predictions made using this model are more likely to be inaccurate. This indicates that the trained model lacks robustness, as it is overly sensitive to the noise in the data. When we train a model using a dataset with reduced noise, even though the number of data points decreases, the resulting curve tends to have better generalization compared to one trained on a noisy dataset. In other words, we end up with a better model overall. This improved generalization enhances the model's robustness, as it becomes less sensitive to variations in the data. As a result, the model performs better on prediction tasks, offering more reliable and consistent outcomes. In machine learning tasks, there's a persistent challenge. We often don't fully understand why a machine is able to perform a task so well. For example, when faced with a problem like what is 1 plus 1, we can intuitively arrive at the correct answer, but if we dig into the details, we might struggle to explain exactly why the answer is 2. Similarly, through training, we enable machines to solve problems effectively, but in many cases, we don't know why the machine performs so well. This lack of understanding isn't an ideal situation. We want to comprehend how everything works so that we can predict risks. Otherwise, people may hesitate to use our trained model, fearing it could harm their business. If the dataset has a clearer overall trend, it can help us better understand the machine learning task, which in turn enhances interpretability. This improved understanding builds confidence in the model and its predictions. Finally, let's consider some common reasons for using data binning. By applying data binning, we transform continuous data into discrete data by dividing it into intervals and assigning a representative value for each interval. This process can reveal nonlinear patterns in the data, increasing its distinguishability. This, in turn, helps in training models to better differentiate between data points. Additionally, in today's machine learning landscape, we have more powerful nonlinear models, such as neural networks in deep learning, which can leverage these patterns effectively. Let's look at one last example. Please ignore the legend in this figure. This is a result from one of my projects, and we don't need to focus on the specific meaning of each curve. From the x-axis, you can see that this small figure contains over 35,000 data points. This makes each curve look more like a shape than a single line. This is a common issue in machine learning when dealing with large data sets. This kind of figure makes analysis difficult. For example, in this case, the curves overlap with each other, making it hard to distinguish them clearly. I added transparency to the figure to help, but it's still challenging to analyze and draw convincing conclusions from such a cluttered visualization. I applied data binning to these data points and generated this new figure. Here, I grouped every 400 data points into a single group and used the average value of those 400 points to represent the group. Through data binning, we can now clearly see the overall trend of each curve, making it easier to compare them and draw more convincing conclusions. Data binning is especially helpful when you're dealing with large datasets and struggling to identify the overall trends. It can often reveal insights you might not have noticed otherwise. Now, let's take a look at the categories of data binning. Generally, data binning can be divided into 3 main types: equal width binning, equal frequency binning, and custom binning. First, we have equal width binning. This means dividing continuous data into fixed size intervals and then identifying key properties within each interval, such as the mean or mode, to represent the entire interval. This approach helps smooth the data by summarizing each interval with a representative value. For example, in this case, I divided the continuous range from 0 to 10 into 10 intervals. Here, we don't care how many data points are in each interval, so some intervals might contain more data points while others might have fewer. This approach focuses solely on dividing the range into equal width intervals without considering the distribution of the data points. Another common approach is to use equal frequency to define bins. For example, in this case, I can group every 400 data points into one bin and calculate the average of those 400 data points to represent the group. This method ensures that each bin contains the same number of data points, making it a balanced way to categorize the data. Finally, there's custom binning, which relies on human knowledge to analyze the dataset and create rational groupings. For example, if we're categorizing people by age, we might divide them into groups like children, teenagers, adults, and seniors. In this case, the number of people in each group may vary, and the range for each group might also be different. For instance, people often define seniors as those aged 65 and older, without specifying an upper limit for this group. Custom binning allows for flexible and meaningful categorization tailored to the specific context of the dataset. When using data binning, the first step is to determine how to define the bins. This involves deciding whether to use equal width bins, equal frequency bins, or rules specifically designed based on domain knowledge. Next, we'll need to write a simple piece of code to implement data binning. For most binning rules, all we need to do is iterate through the dataset once and apply a conditional statement to classify each data point into the appropriate bin. From a logical structure perspective, defining the bin step 2 and assigning data points to the bin step 3 should be treated as separate steps. However, when implementing this in code, we can often combine these steps. This means we can define the bins and assign data points to them at the same time, making the process more efficient. Finally, we need to use the newly created dataset from data binning to continue with the machine learning task. There's no need to delete the raw data, just proceed with the new dataset created through data binning. In this course, it's important to understand the logic behind data binning and be able to implement it. I won't go over a step-by-step example here because data binning is relatively straightforward, and you've likely covered the technical details in previous computer science courses. Finally, let's go over the advantages and disadvantages of data binning. For the advantages, they are closely tied to why we use data binning in the first place. Data binning helps reduce noise, making it easier to uncover hidden patterns or highlight the overall trends in the dataset. This can lead to better model performance with less training time. Additionally, a dataset with clearer patterns improves interpretability, making it easier to understand and explain the results. As for the disadvantages, the most obvious one is that data binning removes some data points, which inevitably leads to information loss. If the lost information is purely noise or unimportant, it won't significantly affect the machine learning task. However, if critical information is lost, the entire task could fail. Another downside is that defining the binning rules introduces human bias, which can increase the risk of creating a biased model. Lastly, if the dataset follows a normal distribution, using methods like the mean to represent a bin may have minimal impact. However, if the data points within a bin are too random and lack a clear distribution, this indicates that each individual data point is unique and valuable. In such cases, we should avoid arbitrarily removing or balancing away their uniqueness. In this video, we took a close look at the logic behind data binning. Implementing data binning isn't particularly difficult, but it's important to understand why we need to perform data binning and the common techniques used for it.